The human brain is one of the most powerful tools on Earth. It's helped us build cities, unlock the secrets of atoms, and send rockets to other planets. But as smart as we are, some things still leave us scratching our heads like paradoxes. See, our minds are wired to understand the world in a logical, cause and effect kind of way. But paradoxes, they flip the script. They hint that reality might not work the way we think it does. And now, after decades of confusion, some physicists say they may have cracked one of the weirdest paradoxes out there. A mystery that's been lingering for over 50 years. But have they really solved it? And what other paradoxes still mess with our understanding of the universe? Let's dive into one you've probably heard of, the Fermi Paradox. Back in the day, Enrico Fermi, an Italian physicist and the mastermind behind the world's first nuclear reactor, asked a simple but chilling question. Where is everybody? Given the age of the universe and how many stars are out there, Fermi figured we should have already encountered intelligent alien life, or at least found some sign of it. After all, Earth and our Sun are part of a relatively young planetary system. If interstellar travel is even remotely possible, shouldn't someone or something have visited by now? Some argue it's not a true paradox. Maybe we just assume intelligent life is common. But here's where it gets interesting. The Drake equation. Formulated in 1961, the Drake equation is basically a cosmic guest list. It uses 7 different factors to estimate how many detectable alien civilizations might be hanging out in the Milky Way. Early versions suggested there could be millions of Earth-like worlds teeming with life. The catch? Back then, we hadn't found any planets outside our solar system. Nada. But everything changed. Fast forward to 2020. Thanks to NASA's Kepler Space Telescope, scientists now estimate there are over 300 million planets in our galaxy that could be similar to Earth. These are rocky worlds orbiting sun-like stars, sitting in the so-called habitable zone, where liquid water and maybe life could exist. Here's the wild part. Planets aren't just common, they actually outnumber stars in the Milky Way, and the search is far from over. The James Webb Space Telescope is already in action, and it's designed to take this quest to a whole new level, scanning distant worlds for signs that we're not alone. We'll have a full video on that coming soon, so don't go anywhere. If the truth is out there, we're getting closer than ever. Now that we've got a clearer picture of just how many planets are out there and how many of them could support intelligent life, one huge question still haunts us. Why is the universe so quiet? With all the possibilities for advanced civilizations, you'd think someone out there would have said hello by now. Maybe we're on the verge of hearing that call as our technology gets better. Or here's a wild thought, maybe they've already been here and we just don't realize it yet. In recent years, there's been a surge of unexplained UFO sightings, some of them even acknowledged by government agencies. Could it be that extraterrestrials are already among us, watching silently? If we ever get solid proof, something undeniable, it could finally solve one of science's most puzzling mysteries, the Fermi Paradox. But that's not the only mind-bender out there. Let's talk about one that really plays with reality, the Bootstrap Paradox. This one dives into the strange world of time travel. It asks a question that breaks your brain. If something from the future is sent into the past, where did it actually come from? It's a popular theme in sci-fi movies like Terminator, Doctor Who, and Bill and Ted's Excellent Adventure. All explore versions of this paradox. So, here's a fun example to wrap your head around. Imagine you're a time traveler. Before you head off on your big journey, you swing by a bookstore and buy a copy of Hamlet, the classic play written by William Shakespeare. Then you travel back to 1600s London and hand the book to Shakespeare himself. Shakespeare reads it, loves it, and publishes it as his own. Centuries go by. That same book is printed over and over, eventually ending up in the very bookstore where you bought it. So, who actually wrote Hamlet? You didn't. Shakespeare didn't. The book just existed, caught in an endless time loop with no real origin. That's the Bootstrap Paradox. A loop where cause and effect blur together until you can't tell which came first. And while we're on the topic of time travel trouble, here's another classic, the Grandfather Paradox. Let's say, purely for the sake of a thought experiment, you love your grandpa. We know you travel back in time with the intention of preventing your grandfather from ever meeting your grandmother. In doing so, you've just made sure your parent was never born, which means you were never born. So if you never existed, then who went back in time to stop your grandfather in the first place? It's a paradox that breaks logic. By changing the past, you erase the very person who changed it. It's like pulling the rug out from under reality itself. These paradoxes don't just make for great movies, they challenge how we think about time, identity, and even existence. And with new discoveries and advanced telescopes like the James Webb peering deeper into space than ever before, who knows? Maybe one day we'll not only solve these paradoxes, but live them. Stay tuned. The universe might not be as silent or as linear as we think. Some scientists think that if you went back in time and changed something major, like stopping a war or altering history, you wouldn't just change your own timeline, you'd actually create a brand new one. Or maybe even jump into a whole different universe. Oh, and if you missed our deep dive into parallel universes, the link's in the description. Definitely worth checking out. One of the most talked about versions of the time travel paradox is this. What if you went back in time to stop Hitler and prevent World War II? Let's say you've got access to a shiny, high-tech time machine. You program the coordinates, travel back to the 1930s, and eliminate Hitler before things spiral out of control. You've just saved millions of lives, right? Well, not so fast. Here's the catch. If you succeed, you erase the very reason you ever needed to go back in time. With no war, no atrocities, and no global crisis, you never make the decision to time travel in the first place, which means you never went back, which means Hitler wasn't stopped. This is the heart of the paradox. Acting to fix the past erases the motivation that caused you to act in the first place. Now, according to some theories like the many worlds interpretation, time travel might not actually change the past at all. Instead, it could spin off a new timeline. So, in one reality, Hitler still rises to power, but in the new one, he's gone. Both versions exist just in separate universes. But here's the twist. You might have just created a timeline that's even worse. And if that didn't melt your brain, try this one on for size. What happens if you send something physical back in time, say, through a wormhole? This is where legendary physicist Joseph Polchinski comes in. He's best known for his work in string theory, but he also cooked up a fascinating and seriously trippy thought experiment. Picture this. A billiard ball is launched into a wormhole. If it keeps its current angle and speed, it'll exit the wormhole in the past, but in a position to collide with its younger self, just as it's about to enter the wormhole. Boom. That collision knocks it off course, meaning it never enters the wormhole to begin with, which means it couldn't have come out to make the collision in the first place. Paradox. But wait, some clever physics students found a workaround. What if the ball comes out at just slightly the wrong angle? Not enough to fully stop its younger self, but just enough to nudge it, changing the angle so that it still ends up going back in time and delivers the same small nudge. No contradiction, no paradox. Just weird looping causality. And now prepare to go even deeper into the rabbit hole. There's something in quantum physics known as the observer's paradox, and it will seriously make you question everything you think you know about reality. One of the strangest examples? Schrödinger's cat. A cat that, according to quantum theory, isn't dead, but it's not alive either. Until you open the box and observe it, it exists in both states at once. Sounds crazy? It is. And yet this is the kind of thing that real quantum mechanics says might actually be possible. So yeah, reality might be way weirder than we ever imagined. And we're just getting started. Let's get this straight from the start. No animals were harmed in the making of this thought experiment. It's purely theoretical. And it just so happens to be one of the weirdest ideas in all of physics, Schrödinger's cat. So, here's how it goes. Picture a cat sealed inside a completely closed windowless box. Inside that box, a tiny chunk of radioactive material, a Geiger counter, a vial of deadly poison, and a small hammer. Here's a setup. The radioactive material has a 50-50 chance of decaying. If it does, the Geiger counter detects it, which then triggers the hammer to smash the vial, releasing the poison. The result? The cat doesn't make it. But here's the mind bender. Until someone opens the box, there's no way to know whether the cat is alive or dead. So according to quantum physics, the cat is somehow both alive and dead at the same time. A bizarre superposition of two opposite realities. How can that be? Well, in quantum mechanics, just the act of observing something can actually change its outcome. You can't say what's truly happening until you look. It's like reality itself is waiting for your input. Sounds strange? Oh, it gets weirder. Let's talk about another quantum mystery that has scientists scratching their heads to this day: the double-slit experiment. This is probably the most famous experiment in all of physics. Here's the basic idea. Imagine you've got a wall with two vertical slits in it, and you're tossing tennis balls toward it. Most balls hit the wall and bounce off, but some go through the slits and hit another wall behind it. Simple enough, right? You'd expect to see two clusters of marks on the back wall lined up with the slits. That's what common sense tells us. But when you run this experiment with light, things take a strange turn. Light isn't just a wave, it's also made up of tiny particles called photons. Now, when you fire photons one at a time at the slits, you'd expect them to go through either the left slit or the right slit, right? Wrong. They somehow interfere with themselves, like they went through both slits at once. And the result on the back wall is an interference pattern, like a ripple effect, not just two straight lines. And here's the real kicker. If you set up a detector to see which slit each photon goes through just to observe it, the interference pattern disappears. Poof, gone. It's like the photon knows it's being watched and changes its behavior just because of that. Let that sink in. Just observing something can alter what already happened. How is that even possible? We don't fully know. Not yet, but maybe, just maybe, you'll be the one to figure it out. And while we're talking about brain-melting paradoxes, there's another one even deeper down the rabbit hole: the black hole information paradox. A mystery born at the crossroads of quantum mechanics and Einstein's theory of general relativity. It challenges everything we think we know about space, time, and what happens to information when it falls into a black hole. But that is a story for another time. So here's the big cosmic puzzle. What really happens to information when it falls into a black hole? Some calculations suggest that once something crosses the black hole's event horizon, the physical details about its information could be lost forever. That would mean different objects, no matter how unique, would all end up in the exact same end state once they fall in. Sounds simple, but it's a huge problem. Why? Because quantum mechanics has one strict rule: information can never be completely destroyed. Let's break that down. Imagine burning two completely different letters. Sure, after they're reduced to ash and smoke, putting them back together is practically impossible, but not theoretically. Subtle differences in the heat, smoke patterns, and the makeup of the ash would still hold clues about which letter was which. That's quantum information always conserved, just scrambled. But black holes? They're a whole different beast. They swallow up everything: stars, light, matter, and slowly, over an insanely long time, they leak out energy in the form of what's known as Hawking radiation. Here's the kicker. Hawking radiation looks exactly the same, no matter what the black hole ate. It's like burning those two letters and only getting back a puff of identical smoke. No hints, no trace, no way to tell what went in. That would mean the original information, gone, wiped out. As the black hole shrinks and evaporates, this surface evolves in just the right way to match what we'd expect if information were being preserved and slowly released through Hawking radiation. In other words, something can escape a black hole. It's not a full-on solution just yet, but it's a huge step forward. This mystery is still unfolding, and you can bet we'll be watching it closely. When the final answer comes in, and it will, you'll hear about it right here. So stay tuned. Reality is getting weirder, and we're just scratching the surface.